In the previous two sections, we talked about a special type of sequence in series called an arithmetic sequence. These sequences had a common difference between the terms, and it allowed us to write some rules and look at sums very quickly and easily. A second type of special sequence that we look at is called a geometric sequence. It has a constant ratio between terms. To get from term to term, we are multiplying by the same quantity. So here is a quick example of a geometric sequence. 1, 2, 4, 8, 16, 32. We can verify that this is geometric by looking at the ratio between terms. The common ratio, called R, can be found by taking any term, a sub n, and dividing by the previous term, a sub n minus 1. So let's check this out. We get 2 divided by 1 is 2. 4 divided by 2 is 2. 8 divided by 4, guess what it is? It's 2. 16 divided by 2, it's 2. 32 divided by 2, I'm losing my mind here. I got so bored. 16 divided by 8 is 2. 32 divided by 16, previous term and all, that's 2. I got so used to writing 2 because it is so common in this sequence. Every single pair of terms, we're multiplying by 2 to get there. The way we find it is take any term and divide by the one right before it. So, you claim that there's a nice quick rule for this, like with arithmetic sequences, Mr. Schneck. You're right, I do, guys. And let's see if we can't figure out where that comes from. So if we call our first term A1, and we call our second term A1 times the common ratio. Remember, first term, and we multiply by the common ratio, we get the second one. A2 or A3 would be A2 times the common ratio, but A2 was A1 times R, now times R again, so A1 R squared. A4 will be A3 times the common ratio. Well, A3 was A1 R squared, that's A3, times this other R right here. A4 is the first term times the common ratio cubed. Are we seeing a pattern yet, ladies and gentlemen? Well, if you're not, let me clarify for you. AN is going to be the first term times the common ratio to the n minus 1 power. Fourth term, common ratio to the third. Third term, common ratio squared. Second term, common ratio to the first. Here is our nice, beautiful geometric sequence rule. So let's dive into our examples, rocking and rolling. Seventh term is 13, so A7 is 13. The ninth term, A9, is 52. What values, important word, that means there could be more than one answer, could the common ratio take? Okay. So 13 is equal to the common ratio, or the first term, times the common ratio to the sixth. Cool. 52 is equal to the first term times the common ratio to the eighth. All right, so I'm just using my generic geometric sequence rule, just like we did in the arithmetic section. Go back to this rule all the time. What we have is a system. I'm going to use the substitution method. Elimination method doesn't work well here. So A1 is 13 divided by R to the sixth. We take that, substitute it into the second equation. 52 equals 13 over R to the sixth times R to the eighth. Well, that's over 1. R to the eighth over R to the sixth. That gives us 13R squared. Oh, we can solve this. 52 equals 13R squared. Divide by 13, we get 4 equals R squared. Square root both sides. R equals plus or minus 2. R can be positive 2 or negative 2 and get us this sequence of numbers. Next example, Here we go. A geometric sequence has a first term of 2 and a common ratio -3. Which term has the value -4,374? One thing you'll get to know about these geometric sequences, the numbers get very big very quickly, likewise very close to 0 very quickly sometimes. So A1 is 2, R is -3. The question is AN equals -4374. Well, let's go to our rule. When in doubt, pull out that geometric rule. We know it's geometric because it has a common ratio and it tells us it's geometric. So our term, our output, -4374 equals first term times common ratio to the n minus 1. Now how do we solve this? Do we do 2 times -3? You better be jumping up and down in your seat saying, no, no! Don't multiply those. The -3 is the base. We got to divide by 2, make that go away. We divide by this 2, and we're going to get, oh, I don't even remember off the top of my head what this is. Let's jump to our calculator. -4,374 divided by 2, -2187 equals -3 to the n minus 1. Oh my, how do we deal with this? Well, normally we would take a logarithm, but this would give us log base -3, and oh, we haven't done log base -3. That scares me. What I'm actually going to do is I'm going to go back to the graphing calculator. Remember, we can use our graphing calculator sometimes to solve problems. I'm going to go to my graph. Let's add a graph page. And I'm actually going to graph these equations right here. -2187. Boom, graphed it. Where is it? Well, it's way down here. I'm going to press tab, graph F2. It was -3 in parentheses, raised to the x minus 1. Remember, it's x in the calculator, not n. Boom! There we go. Holy buckets, that's scary. That scares me. What's going on? Well, what's happening is the terms are going plus minus, plus minus, plus minus, plus minus, plus minus. So what we can actually do, instead of looking at the graph and being scared by, oh my gosh, look at all this stuff, the calculator is just playing to connect the dots. Let's go to a table. Split screen table. And we want to find where is the second graph, where is f2x equal to -2187. There we go. After 8 terms. So when x is 8, these are equal. So n equals 8 here. And there we have it. It's a little bit icky to show your work for something like this, to actually produce this graph. What you probably should do, were this an IB exam, would be to reproduce your table n and an, n equals 1, 2, 3, 4, 5, 6, 7, 8, and show that this is -2187, something like that. Because the graph isn't real helpful, since the points go here, here, then there, then there, then there, and the calculator plays connect the dot with them all, and it's just an icky mess. But this table would be justification enough to show that after n terms, we're good to go. Last example for the day. A geometric sequence has a first term of 5,000 and a common ratio of 0.2. Well, think about this. Are the terms going to get bigger or smaller? Well, the common ratio is a fraction, so the terms will get smaller. Which term is equal to 3.36 times 10 to the negative 15th? Correct to 3 sig figs. What that means is that since this is IB world, this 3.36 times 10 to the negative 15, this 0.0000 blah 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 336, that's rounded, ladies and gentlemen. So the answer that we get is probably not going to be an exact integer value. So here we go. 3.36 times 10 to the negative 15th. Do not use that e negative 15 notation here on your paper, people. That's how the calculator handles this. So we write that equals our rule, 5,000 times 0.2 to the n minus 1. Here we go, here we go. This time I'm going to use my logarithms. I'm going to use my skills with logs. So we divide by 5,000. Ew. Probably going to need a calculator to help you out with this. We get 6.72 times 10 to the negative 19th equals 0.2 n minus 1. Now how do we deal with this? Well, we go to logarithms. I'm going to take the common log of both sides. This is one way to do it. There are others, ladies and gentlemen. Please be aware of that. So now we have log 6.72 times 10 to the negative 19th equals, now the beauty is that exponent comes down, and we have n minus 1 times log of 0.2 divided by log 0.2, and we get n minus 1 equals log of 6.72 times 10 to the negative 19th over log of 0.2, add 1 to both sides, and we shove this bad boy into our calculator, and we get that n is it ends up being approximately 25.9991. So n, 26.999. I lie. It's 26.999991. However many nines that is. So n is really going to be 27. Remember, number of terms must be a positive integer, ladies and gentlemen. And with that, I'm out of here.